In this next example, we are going to look at branches of the square root function. So as a quick reminder, a branch, let me just note this is, if we don't require principal square root, this is multi-valued, right? Because every number has two square roots, every non-zero number. So a branch of a multi-valued function like this is another function. I'm going to write f sub 1 to keep the notation consistent with your book. That is continuous, in particular well-defined, on some domain, and well-defined here. Such that f1 assigns exactly one of the multiple values of f to each point z in the domain. So that's kind of a lot. Not a lot's going on here, though. So for example, what we could do is we could say, hey, for the number, I don't know, I want to take the square root to be the normal principal square root that we've been dealing with. And then maybe at negative I want to take the normal principal square root that we're dealing with. Let's see, it should be positive root 2 over 2 minus I root 2 over 2 if we take the principal square root. Now, that would be fine to define our function little f1, but something we wouldn't want to do, so this would be bad, is we wouldn't want to say, hey, okay, I also want to take 1 to the 1/2 to be negative 1. Because negative 1 does square to 1, so it is a square root of 1. But it's going to cause a continuity break, because all of a sudden we're doing principal stuff, and then we do a jump, and we're doing a non-principal square root. So, so the idea is that you single out sort of a piece of f. That piece is called a branch, and you do what you sort of have to do on that piece. So we're gonna investigate this a little bit more, the square root example. What we're trying to rule out is jumping values like this. So where it's normal, 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 and then not the usual square root. So we'll talk about two branches of the square root function. So branch 1 is going to be little f1 of z. So let me label it. Here's one branch of the square root. And so little f1 of z, what we're going to do is we're going to write z in polar form, where we demand that the arguments between negative pi and pi. So then f1 of z should be what? Well, it should be take the square root of r and then half the angle. Now, that's a well-defined continuous function, and we're not going to actually prove it's continuous, but taking the modulus is continuous, taking a square root is continuous, taking, well, this is sort of a connected area, so taking this exponential function is continuous. And I know a lot of people in this class haven't necessarily had a course in real analysis yet, so we're not going to go into all of the details. We could if we wanted to, but this is one of the branches. Okay. Now, I'll give you another branch, and the other branch, it should be unsurprising. So another branch of this guy, write z similarly. We'll call it f2, is negative root r, e to the I theta over 2. So hopefully this idea of branch is not necessarily a new idea. Instead of picking, for example, all positive values when we take square roots for real numbers, we could pick all negative values. That's okay too. Now both of these have this sort of restricted domain, and I just want to remind you some of the language. So if we look at the domain for both of these guys, what we need to do is we need to take our domain and we need to get rid of this part. So this gold line we delete, and our domain is everything else. This gold line is called a branch cut, and it arises when you have a multi-valued function like this. In order to get a single valued function, usually you're going to have to cut the plane with a curve somehow. And if you cut it with a curve, then you have a hope of defining an honest function. And that's the branch cut that corresponds to both of these branches, actually, of the square root function.